All right, so far we've talked about induction. Want to also talk about bond length or strength and electronegativity, hybridization, and electron delocalization as other structural features that can tell you the relative strength of acids between different molecules that may have similar pKa values. The first one is bond length and strength. So I want you to see if there's any relationship between bond length, strength, and acidity. Go ahead and take a look and see if it makes sense to you. So what we're seeing here is that as the bond gets longer and the bond gets weaker, which you should know that relationship already, how does that affect acidity? We're getting more acidic. Okay, so let's take a look. We have HF on one side and HI on the other. I'm going to really exaggerate this. F is smaller so that these two can be closer together, whereas HI, I think of I like a pregnant woman or something, you know. It's harder to hug somebody. This is a long bond, all right? So this is going to make it longer and easier to break. You can also explain this by conjugate bases. If I draw the conjugate base of HF and conjugate base of HI, notice that the negative charge is in a smaller volume of space. And so that makes it much more electron rich and concentrated than in HI, where the negative charge is all spread out because the iodine is larger. So you got more dispersion or diffusion of that electron cloud. So this is going to be a weaker base, so therefore it has the stronger conjugate acid. So the next effect is to look at the electronegativity on the acidity. That is the electronegativity of the atom attached to the hydrogen. So C versus N versus O versus F. See, their electronegativity is really different. See if you can find a relationship between the electronegativity and the pKa. So we're going to look at the extremes here, CH bonds versus HF bonds. And we're going to notice that the electronegativity of these is different. We know from the pKa's that HF is way more acidic than CH4. So what is it about the electronegativity of F that is creating that acidity? So if I draw in sort of the dipoles, this dipole is very large. So the F is really grabbing these shared electrons here. And that makes sense then. The hydrogen would just pop off. It would lose those electrons and float in the solution. So it's easy to see the dissociation here as being a lot greater than dissociation here. In terms of conjugate bases, we can explain this by looking at the conjugate base of CH is the C anion, and then we have the conjugate base of F, which is this fluoride ion. And remember that the negative charge is more stable on the more electronegative atom. So fluoride likes to bear the negative charge more than carbon would because of its higher effective nuclear charge. That makes it more electronegative to begin with. Likes to pull in that negative charge. So the negative charge is happier on fluoride than on carbon. This means that fluoride, and by the way, this is like that. So fluoride is going to be our weaker base compared to carbon in the same situation. And remember, a weaker base makes a stronger conjugate acid. So that's another explanation for this. Now you might wonder, up here we said fluoride was the stronger base, but we were comparing it to something really different in size, and that made a huge difference. So when you see differences in size, you really want to consider the bond length and strength and things that we talked about, the electrons being spread out in the conjugate base. You don't want to look at electronegativity so much because the higher electronegativity doesn't give you the strongest acid in this case. So when size is very different, don't use electronegativity as your explanation. But when size is similar, such as in the same period going across the periodic table, then you can use electronegativity, and there will be a strong correlation between the electronegativity and the acidity. Another factor to consider is hybridization. So take a look at these data and tell me what you think about the hybridization's effect on the acidity. All right, guys, so in this case, you may have noticed that the hybridization changes the bond length and strength. So let's make sure that makes sense. So these bonds are getting shorter, and these CH bonds actually are getting shorter. So that means the bond strength is getting stronger or increasing, but that's making the acidity greater. So this does not help us the way it did before, where we said the weaker the bond, the more the H can come off, and the greater acidity we have. So we can't use that same explanation here. It's the opposite of what you would think, right? So in this case, we need to consider the conjugate bases and how does hybridization factor into all this. So one way to do that is to think about the orbitals themselves, these hybrid orbitals. And think about, well, remember the difference between an s orbital and a p orbital. So the s orbitals tend to be closer to the nucleus. So that means that we want to think about something called s orbital character. So what that means is what percentage of a hybrid orbital is s as opposed to p. So if we go through the calculation, we could do sp3. We have 4 orbitals, s, and 3 p's. So what percentage of that is s? That's 1 out of 4. So that's 25% s. Go ahead and calculate that for these as well. So what we see here is that sp2 has 33% s character, and an sp is 1s mixed with 1p, so 1 out of 2 orbitals is 50% s character there. Well, what does that matter? How that matters is if the electrons are held close, then that means that that base is more stable. If the electrons are out here, they're going to be more reactive. So let's draw the conjugate bases of these and see what effect that has on its basicity. So what I'm doing here is I've removed one of the H's, replaced it with a lone pair negative charge. So these are my conjugate bases we're looking at. And the effect of the S character is on how closely those electrons are held to the nucleus of the carbon. So in which of these cases are the electrons held closest? It's going to be the one with the greater percent S character, S orbitals being closer to the nucleus. So here the electrons are going to be closer than here, and then here they're going to be the most spread out. So the greater the S character, the more tightly held those electrons are, making it less basic. Let's write that this one is less basic over here. The least basic, or the weakest base, because those electrons are not as accessible. So that's going to translate to the strongest acid. And do we see that in the pKa values? Yes, we do see that those have the lowest pKa of the 3. So the moral of this story is that the hybridization affects the acidity of the H's attached. The more S character you have in those hybrid orbitals, the more the hydrogen is able to leave. Because in a sense, it's like electronegativity, and it's how well the conjugate base holds on to its electrons. That makes it weaker, so the conjugate of that as an acid is stronger. The last factor I want to look at is called resonance, and you know about this already. For resonance, I'd like to look at the conjugate bases. So notice that one of these two molecules has resonance structures and the other does not. Do you know which one does? So if you think acetic acid is the one with resonance structures, you're correct because of these pi electrons here. It really helps to draw on your lone pairs to see that. So you can see that there's going to be resonance here. So let's go ahead and look at their conjugate bases, draw the conjugate base of each of these acids, and look for resonance. And let's draw out the resonance structures, practicing with our arrows. All right, guys, so to get the conjugate bases, I'm going to deprotonate these. Conjugate base of this is this. And then I want to show this in resonance, so I'm going to push these electrons over here. And then that puts a negative charge on this O now. And then if I want to push them back to get the other structure again, I can just go this way again. All right, and that will give me this. Now when I look at this molecule, I do the conjugate base by deprotonating it. And then I get, Make that super clear. I like when you guys are clear too. There, that makes a lone pair. And then there it is. Okay, so conjugate base of this alcohol is this alkoxide or ethoxide ion. Acetic acid's conjugate is acetate. Now, notice what effect resonance has on the electron clouds around the O's. So if I have negative charge build up on this O, that makes it a strong base. But what does resonance do? That spreads out the charge over multiple atoms. And so that helps to stabilize this thing, right? This conjugate base. So over here, though, I have no ability to do that. In fact, I'm gaining some electron cloud from this carbon chain. So it's almost going the wrong direction. So this is going to be much more concentrated negative charge. So this is my stronger base. So therefore, my conjugate acid is going to be weaker compared to this one. Stronger base gives me the weaker conjugate acid when this is protonated. Whereas these guys are weaker bases. And I'm going to show you a term called stabilized by resonance. So these are weaker because they're stabilized by resonance. Therefore, their conjugate acid is going to be stronger than the one we're comparing to. All right, use the concept of resonance and tell me which of these acids would be stronger. And then also think of which acid would have the lower pKa. All right, guys, so I'm going to use the same approach of looking at their conjugate bases and then looking for resonance or some kind of difference like size, electronegativity, hybridization, any of the things that we've been looking at. For this example, we're going to take a base and we're going to deprotonate to get our conjugate bases. So here are my conjugate bases that I'm looking at. And then notice for this one that you have resonance. And these are the different resonance arrows that you should now be familiar with doing on your own. All right, so because of resonance, what effect that has is it's basically spreading out the electron density from the O. It's actually spreading it out to the whole molecule. Whereas over here with the cyclohexanol anion, it's all concentrated on the O with nowhere to spread out. So what that does is that makes this my stronger base. In other words, cyclohexanol is weaker as an acid than phenol. Now the second follow-up question was, which one has a lower pKa? So that requires yet another layer of thinking. The lower the pKa, the stronger the acid. So this is my stronger acid, and this one is also the one with the lower pKa. All right, so putting it all together, we're trying to look at structure and many different factors: charge, size, electronegativity, hybridization, and resonance. Looking at all those things and looking at the conjugate bases as well to draw inferences to the conjugate acids and the relative strength of those acids without the help of pKa charts, because the pKa charts are too general and don't tell you the specific values when you're looking at molecules that are similar in structure. So I highly recommend practice on the next couple of pages. Acids and bases, the way that we present this in organic chemistry tends to be a little bit more challenging, especially the conceptual aspects and being able to explain your answers. It's one thing to be able to circle the stronger acid, but it's another to have to explain that. So I really want you to think about that when you practice. All right, good luck, guys.